Imagine you are solving a problem on an array or string. The brute force way is to compare everything with everything else. It works, but it is often slow. Now imagine using two fingers. One finger points to one position. The other finger points to another position. You move them carefully based on what you see. That is the two pointers technique. It is one of the most useful patterns for solving problems on arrays, strings, and linked lists. The two pointers technique means we use two variables to track two positions in a data structure. Usually, these positions are indexes in an array or string. For example, one pointer may start at the beginning. Another pointer may start at the end. Or both pointers may start from the same side and move forward. The important idea is not just having two pointers. The important idea is how we move them. Each movement should help us remove unnecessary work. Instead of checking every possible combination, we use the structure of the data to move intelligently. Many problems involve relationships between two elements. For example, do two numbers add up to a target? Is a string a palindrome? Can we move all zeros to the end? Can we remove duplicates from a sorted array? Can we rearrange a sequence into the next possible order? A brute force solution may use nested loops. That often leads to O of n squared time. But with two pointers, we can often solve the same problem in O of n time. That means we usually scan the data only once, and in many cases, we use only constant extra space. There are three common types of two-pointer strategies. First, inward traversal. Second, unidirectional traversal. Third, staged traversal. These three types are important because not every two-pointer problem works the same way. Sometimes the pointers move toward each other. Sometimes both pointers move in the same direction. And sometimes one pointer finds an important position first, then the second pointer is used later. Let's understand each one. In inward traversal, the two pointers start from opposite ends. One pointer starts at the beginning, the other pointer starts at the end. Then they move toward the center. Usually we call them left and right. This pattern is useful when we need to compare values from both sides. A very common example is checking whether a string is a palindrome. A palindrome reads the same forward and backward. For example, madam. The first character must match the last character. The second character must match the second last character. So we place left at the start. We place right at the end. If the characters are different, the string is not a palindrome. If they match, we move both pointers inward. If the pointers meet or cross, the string is a palindrome. This is inward traversal. Another important use case is finding a pair in a sorted array. Suppose we have a sorted array, and we want two numbers that add up to a target. We place one pointer at the smallest number. We place the other pointer at the largest number. Now we calculate the sum. If the sum is equal to the target, we found the answer. If the sum is too small, we need a bigger value, so we move the left pointer to the right. If the sum is too large, we need a smaller value, so we move the right pointer to the left. This works because the array is sorted. Sorting gives us direction. We know which pointer to move. That is why two pointers and sorted arrays are often a very powerful combination. The second type is unidirectional traversal. Here, both pointers move in the same direction. Usually, one pointer scans the array. The other pointer tracks a useful position. A simple way to remember this is one pointer reads, the other pointer writes or tracks. This pattern is very useful when we want to modify an array in place. For example, moving zeros to the end. Suppose the array is 0, 1, 0, 3, 12. We want the result to become 1, 3, 12, 0, 0. One pointer scans every element. Another pointer tracks where the next non-zero number should go. Whenever the scanning pointer finds a non-zero number, we place it at the tracking pointer position. Then the tracking pointer moves forward. At the end, all non-zero numbers are at the front. The zeros can be placed at the end. This is unidirectional traversal. Unidirectional traversal is common in in-place cleanup problems. For example, remove duplicates from a sorted array, remove a specific value, partition an array, compress characters, filter valid elements. The idea is usually the same. One pointer scans the original data. The other pointer marks the position where the next valid value should go. This avoids creating a new array. It also avoids repeatedly shifting elements. So the solution is usually O of n time and O of 1 extra space. The third type is staged traversal. This one is a little different. In staged traversal, one pointer first searches for an important position. After that position is found, another pointer is used to complete the operation. So the algorithm happens in stages. First, find the key location. Then, act based on that location. A good example is the next permutation problem. The goal is to rearrange numbers into the next greater order. To solve it, we first scan from the right and find the first position where the sequence can still increase. This position is called the pivot. Then we scan from the right again to find the smallest number that is greater than the pivot. After that, we swap them. Finally, we reverse the part after the pivot. Here, the first pointer finds the pivot. The second pointer finds the correct value to swap. That is staged traversal. Let's quickly compare the three types. In inward traversal, pointers start from opposite ends and move toward the center. Use it when you compare two sides. Examples include palindrome checking, pair sum in a sorted array, and reversing an array. In unidirectional traversal, both pointers move in the same direction. Use it when one pointer scans and the other tracks a boundary or right position. Examples include moving zeros, removing duplicates, and filtering elements in place. In staged traversal, one pointer finds an important position first. Then another pointer helps finish the operation. Examples include next permutation and problems where we find a pivot, boundary, or turning point before rearranging the data. So the main difference is pointer movement. Where do they start? Which direction do they move? And what decision controls the movement? You should think about two pointers when the input is a sequence. For example, an array, a string, or a linked list. Also look for these clues. The problem asks about pairs. The input is sorted. The problem has symmetry. You need to compare left and right sides. You need to modify an array in place. You need to remove, move, or compact elements. Or the problem has a stage where you first find a special position, then perform another operation. These are strong signs that two pointers might be the right pattern. Let's summarize. The two pointers technique uses two positions to solve problems more efficiently. Instead of trying every possible combination, we move the pointers with purpose. There are three important types. Inward traversal. Start from both ends and move toward the center. Unidirectional traversal. Move both pointers in the same direction, usually with one reading and one writing. Staged traversal. Use one pointer to find an important position, then use another pointer to complete the operation. The real skill is not memorizing code. The real skill is understanding movement. Once you know where the pointers start, how they move, and why they move, many array and string problems become much easier. So whenever you see a sequence problem, pause before writing nested loops. Ask yourself, can two pointers solve this more intelligently?